Chapter 1, Problem 1.4. So here we have a complex number z given by a e raised to the power of j theta. We have to find the value of dz and also explain what this relation means using a vector diagram. So let us begin by considering a vector z with an initial position of j theta. We begin by supposing that the magnitude a of the given vector z is constant. Then the only way z can vary is by changing its angle. So let the initial position of z be z of theta. That is, z of theta is equals to a times e raised to the power of j theta. Let this be equation number 1. Now if it rotates anti-clockwise by d theta amount, then the new position will be given by z of theta plus d theta. That is, z of theta plus d theta equals a times e raised to the power of j times, so in place of theta we have theta plus d theta, which can be also written as a times e raised to the power of j theta times e raised to the power of j d theta. Equation number 2. Now the differential dz will be given by dz is equals to the complex number z at theta plus d theta minus the complex number z at theta. So we replace the value by using equation 1 and 2. Now that gives us a times e raised to the power of j theta times e raised to the power of j d theta minus a e raised to the power of j theta. So taking a e raised to the power of j theta as the common factor, so that will get multiplied to e raised to the power of j d theta minus 1. dz will be equals to z, where we have used equation number 1, replacing a e raised to the power of j theta with the value z, multiplied to e raised to the power of j d theta minus 1. Now we are going to use the Taylor expansion. So we will expand the exponential function e raised to the power of x about the origin. So that should give us 1 plus x squared over 2 factorial plus x cube over 3 factorial and so on. So similarly, e raised to the power of j d theta will become 1 plus j d theta. So here we have replaced x with j d theta plus x squared. So that will be j d theta squared over 2 factorial and so on. However, we are going to only consider the terms linear in d theta. So that means we are going to consider the first term and the second term and reject all the higher terms, that is the higher powers of d theta. So we should get e raised to the power of j d theta equals to 1 plus j d theta. So let's replace this back into our equation. So we have z times 1 plus j d theta minus 1. So 1 and 1 gets cancelled out. So we get dz is equals to j times z times d theta, which actually is the solution of our differential dz. Now what does it mean? Let's understand it with the help of a diagram. So if we consider the length a to be constant, then the only way the complex number can change is by rotation. So as we can see from the diagram, here we have a complex number z which is rotated by d theta, and the rotation is done in the anti-clockwise fashion. Also, we know that if we have a complex number and we multiply it by some exponential e raised to the power of j phi, that simply means that we are rotating it anti-clockwise by an angle phi. So that means our differential dz is equals to j d theta times z is actually nothing but, here we replace j d theta with e raised to the power of j d theta times z. So dz represents an infinitesimal anti-clockwise rotation. In the second part of the problem, we need to determine the magnitude and directions of the vectors 2 plus j times square root of 3 and 2 minus j times square root of 3 whole square. So we begin by assuming that the vector 2 plus j square root of 3 is z1 and z2 is equals to 2 minus j times square root of 3 whole square. Let us expand z2. So we're going to use the identity a minus b whole squared. So that is a squared minus 2ab plus b squared. So we have 2 squared minus 2 times 2 times j times square root of 3 plus j times square root of 3 squared. So that gives us 4 minus 4j square root of 3 plus j squared times 3, or 4 minus j times 4 square root of 3 minus 3, since j squared is equals to negative 1. So that finally gives us the value of z2, which is 1 minus j times 4 times square root of 3. Now we're going to determine the magnitude of the given two vectors. So we have the absolute value of z1, or the modulus of z1, will be equals to the square root of the real part squared added to the square of the imaginary part. So that is 2 squared plus square root of 3 squared. So that will give us square root of 7. Then the magnitude of vector z2 will be equals to square root of, we have the real part which is 1, so square it and then add it to the square of the imaginary part, which is negative 4 square root of 3. So when we compute it, we get square root of 49, which is equals to 7. And then we finally come to the directions part. So for the first vector, let theta1 be the direction. So that is equals to tangent inverse of the imaginary part divided by the real part. So the imaginary part is square root of 3 and the imaginary part is 2. So we plug in this value into a calculator, and the value comes out to be 0.714 radians. Then we determine theta2, so that will be tangent inverse of the imaginary part, which is negative 4 square root of 3 divided by 1, and this gives us negative 1.424 radians.